We're in Rosen, Discrete Mathematics and its Applications, section 10.8 on graph coloring. And we will cover all the slides in one video, and then I'll do another video where I go through a proof of a related theorem. Francis Guthrie was a student of De Morgan, of De Morgan's law fame, and he noticed that the counties on a map of England could be colored with only 4 colors that none would touch um, on any kind of border. You could have some colors catty-cornered across a, um, you could have red and red like this, but they're not touching across a border of non-zero length. And we can look at this problem by constructing what's known as a dual graph of a map of a region. What is a dual graph? Well, a dual graph is based on a map, which turns out itself is also a graph, where we assign a vertex to every region, and then we have an edge between vertices representing regions that have a border of non-zero length. Okay, here's a couple of maps, and if I want to construct the dual graph, we'll look at the one on the right. I'll create a vertex for every region, and then if these two regions share a border, I'll include an edge between them. And then the other one, the one on the left, also has a dual graph. You can see that the dual graphs are on the right, and this dual graph over here to the right looks very much like the one we just constructed. So that's how we construct dual graphs, so that a vertex will represent a region and an edge will represent a non-zero length boundary between those regions. Okay, now we want to capture the definition of what a coloring is. The coloring of a simple graph is an assignment of colors to each vertex so that no two adjacent vertices have the same color. And then if we want to discuss the minimum number of colors needed for coloring, that is the chromatic number, chi of G, or chi of the graph G. That's the smallest number of colors needed to do a coloring. And this gives rise to the title of our slide is called the 4-color theorem. That's theorem 1, and that says the chromatic number of a planar graph is no greater than 4. That was the thing that had been discovered when looking at the county maps of England. But the proof of this theorem is extremely difficult and eluded mathematicians for over a century. And it was finally completed. It was noticed and stated back in the 1800s and finally proved in 1976. And the proof is controversial because it relies on computer algorithms to check hundreds of cases for how how a map might be organized or might occur. And that is a very important theorem for planar graphs coloring, but turns out that non-planar graphs can have arbitrarily large chromatic numbers. Okay. All right, so here's a couple of planar graphs. One has chromatic number of 3. Another one has chromatic number equal to 4. And notice that here we have red, blue, green, blue, red. All colors are non-adjacent to each other. But if I take an edge and connect it between these two, I can't have these both be red, so I have to add a 4th color, brown. But I would never have to add any other colors to this graph if I extended it to make it a larger graph planar. Here I have blue and brown. I could make that red. Here I have green and blue, I can make that brown, and then I can connect these two and be fine. Okay, let's think about some different graphs. What is the chromatic number of the complete graph with n vertices? What is the chromatic number of the bipartite graph? And what is the chromatic number of the cycle graph with 6 vertices and the cycle graph with 5 vertices? Well, with a complete graph, I have a vertex between, an edge between every vertex. That means I will need to have n colors so that no two colors are adjacent to each other. All right, what is the chromatic number of a bipartite graph? Well, we saw that we could define a bipartite graph with a two coloring. So um, the chromatic number of a bipartite graph is 2. How about C6? Well, with C6, we recall that we could just alternate colors all the way around it. That C6 is itself a bipartite graph. So its chromatic number is 2. But C5, I can't alternate colors all the way around and keep them non-adjacent. I have to add a third color for C5. So their chromatic numbers are 2 and 3. One of the applications of graph coloring, I really like this one, scheduling final exams. So if I create a graph where a course is a vertex and there's an edge between each course that has a common student, if I have a coloring, then I can assign a unique time for each color, and that will deconflict all my tests. And if I can find a coloring that is equal to the chromatic number for that graph, then I'll have an optimal final exam schedule. Another interesting application is frequency assignments. So stations would represent the vertices, and too close of a proximity would be an edge. So stations that are too close to one another should have unique frequencies, and a coloring of such a graph would ensure that unique frequencies assigned to each color would keep stations from talking over each other. That turns out that this is a pretty hard problem. It's a very hard problem. It's an intractable problem. A K-coloring of a graph is NP complete problem to find, and determining the chromatic number is considered NP hard. So remember that NP complete is in a class of problems that if you find a polynomial time solution to one, you'll have found them for all. NP hard is an intractable problem that even if you found a polynomial time solution for it, it wouldn't necessarily affect other NP complete and hard problems. Okay, so problem 41 is a very interesting problem, and it asks you to show that every planar graph can be colored with no more than 5 colors, what I call the 5-color theorem. Now, the proof is in the back of your textbook, and I'm going to work it out on a separate video. And then you have a recommended homework assignment that asks you to prove the 6-color theorem, which is a fairly bit easier version of the 5-color theorem proof. And that is our discussion of graph coloring, and be sure and watch the video for the proof of the 5-color theorem.